Nehemiah, are you ready with the recording? Okay. So, good evening, guys. I had shared a CSV file in the group, so I hope you've downloaded it. If someone wants to follow up with what I'm doing, I can even be copy pasting the codes in the chat. So I'll take you through regression, the first bit, and I thought it would be best if we just started from the beginning so that you can understand, even when we are writing codes, where or why we are writing these codes. So I've written some short notes. I was just trying to simplify the Athena notes. Machine learning is, it involves training computer models to make predictions or decisions based on data or a data set that you have. And with machine learning, you cannot talk about machine learning without algorithms and models. So algorithms, and I was really trying to make it as simple as possible. You think of it as recipes or instructions, basically telling the computer how to learn from a data or data set. And then now the model is like the output from applying these instructions, which are the algorithms. So I have written like a finished cake that comes out of following the recipe. So from there, we need to understand what predictive modeling is. So basically, predictive modeling, we are using mathematics to explain relationships between independent variable and dependent variable. So these are the independent variable are what we are calling the predictors, and the dependent variable is what we are calling the response variable, so that we can be able to create a model that may predict future behaviors over data sets. So we've talked about these variables. Prediction captures the relationship between the X, which we have said is the independent variable, and the Y, which is the dependent variable. And we are calling it independent and dependent because it's sort of like a cause and effect relationship, where the outcomes of Y are based on the given values of this X, which is the independent variables. So when we understand these variables, now we talk about the response variables or the dependent variables, being able to determine what tasks we are to perform. Yeah. So when we say response, the dependent variable or response variables, it determines whether we are doing regression or classification. So for regression, it means if we are doing regression, it means that these dependent variables are numerical. And if we are doing classification tasks, it means that these dependent variables are categorical. Maybe if I can give an example of numerical, I would think of maybe our overall marks for this course is determined by the MCQs that we keep on doing every week. So the overall cost, we would say, is the response variable, because it depends on the MCQ, which is the independent variable, for the outcome. I hope I'm clear there. Then we have an example of a categorical values are, for example, if an individual's income maybe may determine the level of education they may reach, whether high school, diploma, degree. That's just an example. So you see, those are not numerical, they are categorical. So I hope up to there I am clear. Are there any questions? Please give me a thumbs up if you've understood up to there. Okay, thank you so much. So I will move on to how do we train these models. So the models use data to learn about these relationships. And then the models make predictions which are compared to the original response values. So this I just want to brush through it because I think Nehemiah or Ambale or any other person will take us through this. But basically what we need to know is when you get a data set, you will sort of divide it or split it into 80-20, where 80 you'll use it for training the model and 20% you'll use it for testing. So this 20% will sort of be the new data you are introducing to this model to see if it is working accurately. So we go to the model performance of how the model that you've created, how will you know its accuracy? So as we said earlier, we have two categories, that is the regression and classification. So we'll go through this regression bit in this session, and we'll be talking about the mean absolute error, the mean squared error, the root mean square error, and the R squared. So for this other one, I have personally not gone through them. So I don't know if Nehemiah will take us through or whoever. So this I'll just leave it, but I thought it would be useful if we just know that there are different matrices based on the numerical or categorical classification on how to test your model accuracy. So we get into the linear regression. Yes, someone is talking? Okay, we get into the linear regression. So the linear regression basically is a statistical method which allows us to analyze the relationship between dependent and independent variables. So this is why we get to interact with the line of best fits, where we are fitting a straight line to a set of data points so that you can be able to describe these relationships. So this line of best fits, we get it by using this equation. So this equation helps us to get the perfect position of this line. So we use this equation, and basically the y represents the dependent variable and x independent variable. And then we have the m, or the coefficient. This is the slope of the line, where it represents a change in unit y per unit x. I don't know if I'm making any sense. Yeah, so for every change in x, it affects Y. So this
Lauren,
yes.
let me just try to explain that one.
Okay, thank you.
On the you're welcome. On M is the slope of that line.
Yes.
So it represents per unit change, as in 1 unit in M. If for example M changes per one unit, how much does it affect the Y? Is it 0 point something? Is it 2? Is it 5? So that is basically what that M does. Sorry for interrupting.
Yeah, thank you so much, Ambalo, for that. Yes, that's exactly what I was trying to explain. So it tells us how the line, the steeper the line, the more if any small change of X, it will have a very huge significant change in Y. So the M basically shows us the steep of the slope and also tells us the direction. So when we see this graph here, this positive or negative is caused by the M or coefficient value. Then we go to the C, which is basically the intercept. This represents a predictive value of Y where X is 0. So basically where this line meets with our line of best fit meets with the Y axis. So up to there, I hope you've all understood before we proceed. Any questions? Okay, thank you. So I came up with these steps as I was doing the linear regression model, the example that we were given in Athena, but now I came up with that CSV that I've sent you, and I tried to follow the same steps to basically come up with a model. So I wanted us to do this together using the CSV that I had sent. So the first step is to import the necessary packages, then we load the data set, and then we conduct an EDA. So we have this, we import these packages that we are meant to use in our example. And then I've just loaded the CSV that I had shared with you. So we can run this. I think everyone understands this because this is what we've been doing. Yeah. So this is our data.
Lauren.
Yes.
Yeah, sorry for taking you back. Do you mind explaining the last package from Matplotlib import RC? What is RC?
This basically picked from what? There's an example that we were given in Athena, but I googled it and it's what? Runtime configuration. I think it helps us to do what? To be able to have these colors in our lines and our plots. I don't know if I'm right. Maybe someone can help, Nehemiah or anyone else, but that's how I understood it. It's runtime configuration. Anyone else who has an idea of what this RC does? But that's how I understood it. Nehemiah, if you can help, or Emmanuel, you're trying to speak.
Okay. I also googled it, but I think it's not like the colors. I think it's just that black font. It said like something like that black font. So it's not really the
Which
other
black
colors. I think when you check on the graph,
Mm.
the graph that was earlier in the modules, I think we'll get it there.
Okay. Okay. Thank you, Manuel. Thank you, Mama. Is it clear? I don't know who asked that question. Was it Ian?
Yes, it is. Yes, it is. Thank you.
Okay. So this is our data frame that we are going to be working with. So I had a few lines of code to perform the EDA. We are not going to get deep into it because of time, but the normal DF describe that tells us our mean, our standard deviation, and minimum. These are the quartiles and the max and the counts. Then next, let's just go back to our steps. We are still on EDA, but first I wanted to change these column names to be X and Y so that it can be easy for us to plot when we are talking about the dependent and independent variables. Then now we just want to see how our data frame is when we plot it in a scatter plot. So we can see already, we can see a linear relationship sort of. Yeah, I hope you all agree. So then from there, now we need to change this data frame into NumPy arrays so that we can be able to perform mathematical operations for the linear regression. So how to change it? This is the code for changing it into arrays. And if we want to check, let me just see, for example, if it has changed, you see. So we have our arrays. If you want to check for Y, you can see that it has changed. So the next step, so we are where we change data into NumPy arrays. Then now we ensure that our X array is in 2D. So I've seen this question being asked in our webinar, and I'm not sure if I've gotten why we are changing only the X into what? Into 2D. Anyone who has an idea of why we are changing it into 2D, only the X? Anyone?
Okay, if I can chip on this.
Who can explain?
Okay, while fitting the model. Doreen,
Sorry?
can you hear me?
Yes.
I'm trying to make a point that when fitting the model, when it was programmed that the first variable should always be converted into 2D. That is according to the who created the module. Then, if I would call it a module, it was supposed to be turned into 2D to enable it at least recall each value, because the model is trying to run to fit the model from first value. That's the main point. If it is scoring the model, it is scoring the data from the index. So that's what I got when I searched. Maybe it would be of help to someone else.
So is it the first variable or is it the independent variable?
Okay, let me see if I can touch on that a bit, right? So what happens is that once you call out the values from the data frame, right? They are in arrays, meaning that they are not in the matrix format, right? Maybe a 2x2, they are just in series, meaning they just have an ID and the data itself. So they are not in any format. So when you try to change it to 2D, when you say you're changing it to 2D, what we are basically doing is to have like a matrix, maybe 1x2 or 2x1, or 2x2, right? Because a series is basically 1x1. So in order to change it to 2D is why we now call on the np.newAxis. It's already a 1x1. So we are calling in a new axis to make it a 2x1 or a 2x1 data frame or a 2x1 axis, so that you can now work on those data, because everything works like a kind of matrix. You know how we've been doing it before. So the series will not be able to work like that. So in order to do all those computations, we need to make it like a matrix. I think that's it in a nutshell.
Okay. Thank you. Thank you so much, guys. That I think is clear. And then after changing the X into 2D array, now we initialize the linear regression model. So this is the code. I don't know why it's doing an error.
Lori,
Yeah.
did you import the linear regression package up there?
No, she didn't.
I did not.
Yeah.
So you have to import it. So
So you have
import.
they call it Skype. Yeah. Go ahead, Ray.
Someone
Okay.
to guide me.
So from Matplotlib, right? I think
Is it
so.
from Matplotlib?
Yes.
No, linear regression.
Oh, no?
It's not from Matplotlib.
It's not from Matplotlib.
Yes. I hope you have improved. You have installed. Is it Scikit-learn?
Yes, I have.
Sorry, from Scikit-learn.
Yeah, exactly.
From Scikit-learn. Dot model selection. No, we are importing linear regression.
Yeah.
No, there's
something there.
no, there's something after Scikit-learn, like linear
model
underscore
model.
Yes, linear underscore model. Exactly.
like that.
Exactly.
Yeah. Okay. Thank you so much, guys. Okay then. So after initializing, now we fit the model into our data. So that is this step. Where is it? Fitting the linear model into our data set. So,
Can you run through the steps again to up to where we are again? Can you just rerun it?
we've imported the necessary packages. Then we've loaded the data. Then we've conducted a bit of EBA. Then we've changed the data into NumPy arrays. Then we've changed the X or independent variable into 2D. Then we've initialized the linear regression. And then we are fitting the linear model that we've been initialized into the data set. So this is where we are, and then now we go to predict using this fitted linear model.
Lorraine,
Right. Yes.
do you mind showing us how our data set will look like after converting the X array into 2D?
Okay, let's see. Where did we convert it here? I think it will have double square brackets. You've seen?
Yes, thank you.
Okay. So we've fitted our model into the data set. So now we are trying to see our values of M and the C before we predict, just to have a feel of how it looks like. And I'm getting another error.
Did you run the cell before that?
Have you run the cell above? Okay, yes, now it's working. I had not run this one. Okay. So we are seeing our M is 0.84 and our intercept is around 14.68. So now we go to the predicting our Y values. So let's just run this. I hope you guys are understanding these codes. So these are our Y values. These are the values that we will use to plot the line of best fits. I hope that is clear. So for the next step, let me just go back. Sorry for taking you back and forth. Is now we are plotting our line of best fit. So this is the code. I don't know if anyone wants me to explain this. So we are plotting a scatter with our X and the X that we had changed into a 2D and our Y. Then we are plotting our line using this Y values predicted that we got, and then we want the line to be red. And then now we are just labeling our graph. So this is how it looks like. Any questions up to here?
Yes, I just have a comment, or rather something very interesting that I discovered is that you don't need just scroll up the code above this. Yeah, there. No, the code.
This one.
Yes.
Mm-hmm.
I noticed that I don't need the very last line of code, tlt.show, for the diagram to display.
Okay. I did not know that. Anyone else? Anyone
So
who can. Uh-huh.
maybe just to point something.
Mm-hmm.
Here we are talking about the line of the best fit. The best fit. If you try to look at that line, why is it a line of the best fit? Because it like goes through most of the points. You can see we have all those points. The blue dots, those are the x variables. So it tries to go through most of them. That is why it is known as the line of the best fit. Hope guys have understood. I know not all of us have come from economics background.
Ibrahim,
Yes.
trying it, this line of best fit is normally drawn from the predicted value. So it is not normally from the data itself, but from the value we predict. The model tries to fit a line from the value it predicts itself. It is not normally from the real data itself.
Okay, maybe just to understand, you see those blue dots?
Yes.
Are those predicted values or they are the real values?
From
the blue dots.
The blue dots.
Yeah, are those predicted ones or they are the real ones?
The real ones.
The real ones. Those are the real ones.
Yeah, that is why I'm trying to say that lines tries to go through most of those values. I don't know if I'm making sense.
I think both of you are making sense, right? So the principle is simple. You see, the reason for the prediction is to see how close we can get to the actual data, right? So using the line of best fit, Ibrahim is coming from the mathematical and economic point of view that, okay, if we had a real set of data, we're plotting it manually, we will draw the line that try to go through it. But the machine method, right, what it does is that it takes some part of the data, from the real data, uses the real data, uses some part of data to predict the line that should go through using what, I don't know who mentioned that, that uses predicted values to draw the line. So it now superimposes it on it. And that line should be the line closest, to the actual real data. So both of you are right. It juxtaposes the knowledge of what both of you are saying to achieve this.
So sorry, I stand to be corrected. If you are drawing, even if it's a graph manually, you do not consider. You just draw from the 0 point. If you want a straight line graph, so you are just drawing from the 0 point upward. It does not really target. It doesn't have business on the data per se, but when it's drawn, anyone that comes to it, that's where you now do your consideration. So what I'm trying to explain is that it's not targeted to the blue lines. I don't know, but that's from my own, let's say, graph drawing knowledge. It's not targeted at the blue line. It's just a line that goes there, and with that, you can now explain what happens, whether it's decreasing as the values increase or is increasing. I don't know if I get it correct.
Ijama, it's true in mathematics you draw the line, but you always follow the data. And this is the simple reason why. If the data is following a particular trajectory, right, you try and see if you have already been able to say, okay, this data is going to a positive direction or it's going to a negative direction. You won't see data going through a negative direction and, just draw a line directly from the center sometimes the line of best fit does not come from center of origin 0. So that's why we say it follows the data. It's the shape
Yeah.
of the data it follows. If you look at this graph, for instance, you will see that the origin of that red line is not 0. Some data,
Yes,
the origin will be 0.
sorry, you are getting me wrong, Ray. Sorry. So why I stated that is because of what I think Ambale said. So I was trying to get that understanding because from what I used to know, right? He said even if it's drawn manually, that you have to. I don't know. That's what I heard. That was why I now said no. Even if you're drawing manually, you have to follow the you don't consider the values itself. Now, if you're considering the shape, or from the point of say it's not from 0, it's from 40, the line just goes straight. You're not considering so you determine the result from the affected dots. Like we are trying to get the line of best fit, which is we have I don't know how to explain this, but I'm trying to say that the data is not considered. The line just goes on its own, and it's with the line that you now make your predictions. Sorry, do you understand me, Ray?
That makes sense.
Thank you.
Yeah, and maybe Ray, Ian, and the other guy, I did not see your name, sorry. Please hear this and correct me if I'm wrong. I believe this line is y equals to mx plus c. This is the line that we have drawn, right?
Correct.
This is the line that we have drawn.
Correct.
So we are not just drawing any line. We have calculated, we have predicted the values of y using that formula, y equals to mx plus c. And we were able to get our intercept c, which was at 14 point something, and then our m, which is, just scroll down a bit, Laureen. Our m is 0.8 something. So predicting that line of y equals to mx plus c, I believe we have used the real value of x to predict y. So this line
Ibrahim,
is yes.
If you look from how Laureen has done it, blt.plot x, then Laureen, hope you're there.
Yeah.
blt.plot, where you have plotted the line.
Yeah, here.
Yes. That's what has been. Lazarus. But the point I'm trying to make, from the plot you have done it at x and the y, the value you are predicting. So what the model is trying to do, or what it has done, it has fitted some values which you have called it y value predicting, which will provide the least error, which are the line we have, the error between the line and the distance between the line and the blue point, those blue point is always less. That is the best fit. We have used the predicted value. We draw the line using the predicted value because the model did, it predicted some values which will provide the least error when the line is
Lazarus. I believe your name is
It's not Lazarus. It's Karik. Don't let me write my
Okay. I've split my screen so I cannot see you talk. So, Lauren, can you just go to that graph, because he is explaining a very important aspect, that the errors. So maybe if he can come back again as people watch this graph and then say that again for people to internalize.
Okay. What I'm trying to say is that when Laureen called the linear regression model .fit, LM.fit, what it on what was happening on the back end, the model trying to fit some values which when inserted on our scatter plot, on our little scatter plot, the little data scatter plot, those points will always have less distance from the main point that we have, the data that we have. So whenever we plot a line between those points, the beaten point, the line will always, the distance between the line and the point will always be less. That's the less, the less, can I say the least distance we have?
Yes.
Yes. And this is always determined by, when splitting the data, the random state. When you try changing the random state, it is normally L, because when I was coding, I tried to use the random state at 0, and I always found that at 0 it always provided a good yes, a good fit at 0, at random state equals 0. Yes.
Onesimus, you're not audible enough, but I would like to know what's the point of contention.
Okay, what we are trying to explain was what are the points used to draw the line of S. We have come to.
I can still not hear you clearly.
Okay, maybe Ian, if I try and help Onesimus, we were just like Onesimus and I were just like trying to explain these blue variables and the line for just people to understand. So maybe if you can also say something on the same here.
Yeah, Lorraine, do you mind going back to where you first wrote this equation?
Which one? The one for plotting or?
Yes.
Yeah.
The equation y is equals to mx plus c. Did you like do it physically, manually?
No, I did not. So let me just try and explain. So if we try and do it, I was avoiding that route of doing it manually, because maybe it will confuse people. But since we have Python, I believe that the equation y is equals to mx plus c is happening here, right? So that we can get these values, and these values are the ones that we are using to plot this line. I hope I'm saying the right thing. So the y is equals to mx plus c is conducted here. If we go the other route, it is a very, very long equation. We have to get the m, and then we have to get the c, and then now we start getting the values. But now with these packages that we've imported, it makes our work easier, and the y is equals to mx plus c is happening here. So that now we are getting these values, and these values are the ones that we are using here. Now we've said we plot our normal scatter plot, the one that we had plotted up there. And then now we want in this scatter plot to have our line of best fit, where it minimizes this distance between our predicted model and the actual values. So with this performance of the y is equals to mx plus c, this is the best fit in this our scenario. So I don't know if Ian, I'm clear.
Yeah, I believe by the way, whatever you've explained is totally clear. I think the point of contention between Onesimus and Ibrahim was Ibrahim using the word line of best fit is a line that passes through majority of the points, which is ideally correct when you look at it in a mathematical perspective, just as Ray has said.
Yes.
But if you're looking at it in a machine learning perspective, like you want to use this line of best fit to predict, the dependent variable, the line of best fit will not necessarily pass through majority of the points, but it will pass along. It will pass through
It will be the best position.
points. Yeah, the points. In that, for those lines, even if it passes through like 2 points, like how we are saying here, the most important thing is the distance between that red line and various data points. The main goal is to have a very minimal distance between
Yeah.
the red line, and the data points, which are in blue.
Yes.
That's
Yes.
the goal. The lower
Yes.
the distance, which we are calling residual or error, the better, since it means
Exactly.
that it will be close to the data points.
Yes.
So now, what people need to know is that we are simply interested in the distance between the blue, which are the data points, and our line. Not
Yes.
necessarily majority of points passing through the line. The lower the distance, the better.
Yes, and that is what the y is equals to mx plus c is doing. It's giving us the best position this line can be to minimize these distances. So this is the best it can be at. So is there any question, or we can move on? I hope it is clear now. Okay, thank you. So our next step is to do what? Let's just go back to our steps. We have already plotted the line. Now we start performing the model accuracy. So I've heard Ian talking about the residual, which is basically the distance between our line of best fit and the actual data points. So you can see the formula here, which is y and minus our predicted values. And then we are trying to, here I just try to plot the residual values to see. In our notes, there was this bit that was saying, if you want to know your model is accurate using the residual plot, it should be randomly distributed along the horizontal x value, this one here. If it has a shape somehow, it means that your model is not accurate. I hope I've not confused anyone. Is it clear up to there? So a random scatter around the horizontal axis indicates that the regression model is appropriate for the data. And if we have any non-random patterns, it means that the model is not appropriate. So we can see ours is randomly scattered. Any questions there? Okay. So we continue with our next matrix, which is the residual sum of squares. So that is this difference between the line of best fit and the actual data. Then we square, and I read somewhere that we are squaring it to make the numbers positive. So that's why we are squaring it. So for this value, it should be as minimal as possible for your model to be accurate. So let's see. So it's 557. So for this, I understood that it depends with the context or the data set that you're trying to investigate. So, but it is not an ideal. You can't only use the RSS to predict whether your model is accurate or not. You need to conduct more metrics. So I don't know if there's any question here. Have we understood? We move on to the next metrics. Okay. So we are moving on to the MAE, that's the mean absolute error. And basically, we are just doing the averages of the absolute values of the residuals. So we are taking those residuals, which is the difference between our line of best fit and the actual data, and then we are getting the average. So this is the code for getting the MAE, and with MAE is still the same. The lower the MAE, the better your model. Then we get our mean squared error. So for our mean squared error, it's basically the average of the squares of the residuals. So you've gotten the squares of the residuals, and then now you conduct the average. Then we have our root mean squared error. So that is basically the square root of the MSE. So the lower, again, the better. Then we do our R squared or our R score, and it basically indicates how well the independent variable explains the variation in the dependent variable. Any questions? Okay, let's run and see how our values are. So we can see our mean absolute error is 3, which is quite low. And then our mean square error is 19. And our RMSE is 4. And our R squared is 0.9. And for this R squared, the more it is closer to 1, the accurate your model is. So I hope up to there we have understood. So if there are no, do you have any questions before now we continue to the key takeaways?
Yeah, I think there's a question in the chat, but this one, Ray and Ian, you will forgive me. I'm sending this question to you from Charles Nganga. Charles Nganga asks,
what is the question saying? I can't see the chat.
Yeah, Charles Nganga is asking, does it mean when we are using line of best fit, does it mean when we are using line of best fit is used to assess the accuracy of the model rather than prediction? Meaning we can do prediction without line of best fit. This one I'm throwing into Ray and Ian because I'm also trying to think about it.
I have not understood the question. Let me just try and read.
Maybe Charles can talk because I see his hand. He has raised his hand.
Okay, my question is, when we are using the line of best fit, does it mean we are assessing the accuracy of the model and we doesn't need it to do the prediction? When you are like for example, if we are doing for a prediction for something, we don't need to use the line of best fit. Is that we can say that?
I think, Charles, let me try and answer, and if I'm wrong, if anyone can correct me. The line of best fit is the model that we are using to make predictions. So this line of best fit is what we are trying to check if it's accurate. I don't know if I've answered your question. So this line of best fit is the model itself that we are trying to use to predict. So you need this line of best fit to predict. But before you predict anything, you need to test if it is accurate. That's why now we are conducting all those metric tests to see if this line of best fit can really do predictions if we introduce it to a new set of data.
Okay.
Yeah, and maybe just Lauren, can you just go up to where we had the real values of x?
This
Up. I think that's not here. The real value of x, the one up dot header.
after we've changed it into
No. Not even before we change that.
okay,
Can you just
here.
scroll?
Let me just add a code.
Yeah, can you see the x values?
These are the x values.
Yeah. So these are the x values, and this is what we have fed into the model, and we have used these ones to predict the y values. So just like Lauren has said, Charles, what if we have, let me guess a number here. Do you have any number like 100 in this data set? X is 100. Is there any? No. So that model is trying to predict the values of y. So what if we have x as 100? That is why we have come up with the line of the best fit, which is y equals to mx plus c. So we'll just like replace that x with 100, and because we have our m value and our c value, we'll be able to predict the y value. Hope I've explained something.
Is it clear? I hope it.
Yes.
Was it Charles? Okay. So, any other questions
Sorry.
before we?
Sorry. Just to say something to what Charles is saying, right? So all this mean absolute error, MSC, RMSC, all these things we are just trying to do is a way to improve, the model so that it gives us the best, predictions possible. So yes, we fitted it to the data, right? So we are trying to correct for or check for all the errors, around and be able to make adjustments on the line so that at the end of the day, it gives us as closely as possible, if not the exact number, just to give us something as close as possible to the exact thing. So that's what this other part is doing. We fitted the line, but now we are correcting for all those minor errors. Mean absolute error, what's the distance between the true value and the predicted value? Can we reduce it? Can we correct for another form of error? Can we reduce it? So that's what all these ones are doing. So that at the end of the day, it gives us something very close. Thank you.
Okay. Thank you so much, Ray. So we can go ahead and finish up with the key takeaways. So the first key takeaway is that linear regression allows us to find the line of best fit by minimizing the residual sum of squares. I think this is what we've been trying to explain. And then the coefficient, which is the m, it tells us the direction and how steep the slope will be. A steep slope means a small change in x will lead to a large change in y, or a significant change in y. I hope that is clear. Then the intercept represents the predictive value of y when x is 0. That one we discussed. And the fourth one is the mean absolute error is how far predictions are on average to the actual values. And the lower it is, the more accurate your model is. And for the MAE, you'll find that it is easy to interpret and it is less sensitive to outliers, but it is not it is not ideally used for detecting large errors. So the MSE is average square difference between predicted and actual values. And the lower the MSE, the more accurate the model. This one detects large errors, but it is very sensitive to outliers, and it is not easy to interpret as we are squaring. I hope that is clear. So if we square and we are comparing it to the actual values which are not squared, it might not be easy to interpret. And then we go to the RMSE, which is the root mean square error. It is similar to the mean absolute error, because now it's like we are what is it called, square rooting the MSE, which takes us back to MAE, but is more emphasizing on large errors. It is more interpretable as it is in the same units as the actual values, and it is very sensitive to outliers. Then we go to the R squared, which tells you how well your model explains the variation in your data. The closer your R squared to 1, the closer you are to finding the line of best fit. Then in choosing these metrics will depend with the context of the scenario or the data set that you have. And always check that your data has no missing values, because you cannot conduct any linear regression with a data set that has missing values. So I think that's it. That's what I had for you today. And if I can show you